In this video, we're going to talk more about thermal expansion. We're going to go through two separate equations and talk about two different scenarios in which thermal expansion occurs and why we see certain things that we do. Here's our base equation for thermal expansion. Delta L just talks about the change in length. So it's only typically a minuscule value based upon the overall length of the object itself. This value right here is our linear expansion coefficient. It is written in Kelvin. Since delta T is truly only measuring a change in temperature, it really doesn't matter if we're in Celsius or in Kelvin. But in the end, if you are trying to look for a change in temperature, that's why it's written in Kelvin in the end. So that way you could go back and you wouldn't get a negative number in the backside of trying to solve an equation backwards. L is the original length of the object, and delta L is the change in length. So if we start with something that's 100 meters and our change of length is only 0.1 meter, it would be 100.1 in the end. All right, let's look at a practice problem and see how it all works together. Here we have a steel suspension bridge that's 200 meters long at 20 degrees Celsius. When the temperature gets down to negative 30 Celsius, how much will the bridge contract? All right, so if we look at our equation here, first we have to know that A sub L for steel is going to be 12 e to the negative 6. So that's our constant value that we're going to use and insert there. Everything else just falls right on our line for our equation. So 12 e to the negative 6. The initial length of the bridge is 200 meters. And my change in temperature, remember we always do final minus initial, so it's negative 30 degrees Celsius minus 20 degrees Celsius. 30 minus 20 gives me negative 50. So when we do negative 12 e to the negative 6 times 200 meters times negative 50, we get a change in length equal to negative 0.12 meters. So even though our bridge itself is 200 meters long, the overall change is only going to be 12 centimeters. And since it's getting colder, it's going to contract. You might notice that when you go over some larger bridges, they'll have those, it looks like teeth inside of them. That is put there for the thermal expansion in the really hot and really cold months. Volume expansion, it works basically the same, but instead of one dimension in the x-plane, now we're doing x, y, and z. The thing about volume expansion is this equation, it's not so good for describing the expansion of a gas, because gases expand to fill whatever containers they're in. The volume of the gas depends on the pressure and temperature. When the pressure and temperature have reached the same through the system, we consider this an equilibrium state of the system. So the volume thermal expansion works for a 3D object, like a steel cube. It would expand out in all x, y, and z planes. So solids, not gases. All right, here are two misconceptions or common ideas for thermal expansion. Do holes expand or contract? So let's say you heat a thin circular ring in the oven. Does the ring's hole get larger or smaller? So here is my ring. It's red because it's super hot. Now, inside this radial distance r, now that it's super hot, you would think that, in your head, that this inside wall would expand in the middle, but this is not true. Imagine the ring as a solid coin. If you heat the coin, all parts of the coin would expand outward, away from the center, making it clear that the hole would actually increase in diameter. This is true for all circular and spherical objects. Remember that. All right, last part deals with bimetallic plates. These are very efficient in your house when you're dealing with circuits and circuit breakers. So basically here we have a diagram of a circuit breaker. The bimetallic strip is in the middle, and when it's touching this contact piece, you have created a circuit, closed circuit, current can flow. What happens is when the bimetallic strip becomes heated due to too much current, if I'm flowing 20 amps through there, the metal itself is going to overheat, and if I have no way to break that circuit, my house is going to burn down. Sucks for me. So, with higher thermal expansion rating, what's going to happen is the top one is going to expand more. So this is going to get longer. As this one gets longer and this one stays to the close side, it's going to bend down and away from the contact. So as it starts to bend down and away, in a true circuit breaker, there's like a little divot in here that it falls into and will hold there until you push it back into place. But as this one gets expansive, it starts to slide away from the contact and then falls into that little slot. In order to turn the circuit breaker back on, you have to flip the switch on the bimetallic strip, forcing the breaker back into contact with the circuit. So those are two prime examples of how thermal expansion affect us in our everyday lives.